In this next example, I want to go ahead and take a look at the line integral over C of arctan x plus y squared dx plus e to the y minus x squared dy. And my region C, or my curve C, excuse me, is this curve that sort of goes around the semi-annular arc. So we go kind of from -1 over to 1, and then across the x-axis to 4, and then back up and around down to -4 and back to -1. So do notice that C is simple and closed, and it's oriented counterclockwise. So if we do think about trying to do this integral with respect to computing it as a line integral, we would have to create a piecewise parametrization for this, which we would probably create those 4 different pieces, so the 2 different semicircular arcs and those 2 different line segments along the x-axis. And then we would take those dot products with the derivatives of those different piecewise smooth curves. But then we're also going to have not a particularly nice integral either, because we are going to have those arctan and different pieces in there as well. If we think about Green's theorem, this isn't a particularly nice region in rectangular coordinates, but it is a nice region in polar coordinates. So we might already be thinking that far ahead. Where if I try and put this region R, trying to describe it, let's think about it in polar coordinates, where then R, we could see, well, that goes from 1 to 4. And then theta, we only do a half turn, so we go from 0 to pi. Now, what we need to take a look and think about is, could we also then convert the rest of Green's theorem well into polar coordinates? So let's see what the rest of it would look like. On the inside of the integral, we would end up taking a look at the partial of n with respect to x. So the partial with respect to x of the second component, which is e to the y minus x squared. Well, that's just the function -2x, which is fairly simple. We know how to convert that to polar. And then the partial of m with respect to y, well, then we'd be doing the partial with respect to y of arctan x plus y squared. So that arctan x is just going to be 0, and we're just left with 2y. So we actually end up with a much simpler expression to deal with. So let's try and put this all together. We would have the line integral over C of this whole expression, arctan x plus y squared dx plus that e to the y minus x squared dy. Green's theorem says that we're going to convert this to the double integral over R of that partial of n with respect to x, which was -2x, and then minus the partial of m with respect to y, which was 2y. And we're going to do this integral dA. Now, this is a fairly simple integral, especially if we convert it to polar coordinates. So switching that all the way to polar, then we would have the integral from 0 to pi, and then 1 to 4. We'd have -2x. We're going to replace with that r cosine theta. We'd have minus 2y. We replace with r sine theta. And then remember to switch to polar, we end up with then an r dr d theta. And we're going to be able to do this integral not too bad here. So then distributing that r through, we get 0 to pi, integral 0 to 1, or sorry, 1 to 4, excuse me. We'd have -2r squared cosine theta minus 2r squared sine theta. And then we're doing dr first, followed by d theta. So we'd have the integral 0 to pi, we'll have the 2. The -2r squared will go to -2/3 r cubed cosine theta, and then another -2 2/3 r cubed sine theta. Evaluate that from 1 to 4. D theta. So I'll have the integral 0 to pi. Plugging in 4, we're going to end up with -2 times 4 cubed. So if we do a little 4 cubed, where's my power? And then times 2. And then we'll just put that over 3. So we had 64, or 64, and then times 2 is 128. So we've got -128 over 3. Notice that's in both pieces, so let's just actually factor it out. So that's going to then be times cosine theta plus sine theta. I already pulled out the negative. And then we're going to have minus, plugging in a 1. So when I plug in 1 to those 2/3 r cubes, we're going to get -2/3. So we'll really have plus 2/3. And then again, times cosine theta plus sine theta. D theta. So let's actually just take a real quick second here to factor this. So we've got kind of this front coefficient of -128 and then plus a 2, so we would have -126 thirds, and that's going to be times cosine theta plus sine theta, d theta. And just to double check, let's see, 126 divided by 3 is just 42, so really we just have -42 out front. And then we've got cosine theta plus sine theta d theta. Cosine theta is going to integrate to be sine theta. And then sine theta integrates to negative cosine theta. We're going to evaluate that from 0 to pi. So then I would have -42, plugging in pi. Sine is going to be 0. Cosine theta is going to be -1. So we really have -1. And then minus, plugging in 0. Sine of theta is 0. And cosine of theta is 1. So then let's keep track of our negatives here. So we had really like 0 minus -1, and then we're subtracting 0 minus a +1. So we've got -42 times 1 plus 1. So -42 times 2 is going to be -84 for that line integral. So and this one, again, we kind of recognize that rather than doing the line integral that was given, we converted it to a double integral because we were able to represent that region simply with polar coordinates. We haven't done any examples yet, but we definitely could, where rather than, say, convert from a line integral to a double integral, you could use Green's theorem in the other direction as well. So just take, for example, say the function up above. If it was something where you do have this interior curve is just going to end up being a 0. Well, I guess at that point, then we would just see that the integral is 0 anyway. But if you could see that the line integral is simpler, you could try and find a way of deconstructing the integrand on the inside of Green's theorem and converting it back to, say, a vector field is a possibility. So it's a little more common to go the forward direction of going from a line integral to a double integral, but in theory, you could go the other way as well.